Welcome to another GCBASIC demonstration. This isn't your normal video. What I'm going to do, I'm going to dig into the implementation of a new chip family. I've, this is probably one of the last picks we'll ever be adding to GCBASIC. I can't see that Microchip are going to be releasing many more microcontrollers, and therefore I think we should just do this as a last hurrah. So like and subscribe to the video. This is a new chip family, the initial challenges. And it's going to be quite interesting because it's going to be a voyage of discovery. I will do a set of videos and I will do 20 videos like this. Normally what I do is I do the videos after I've worked out all the problems. So I sort of work through the challenges of getting this stuff working, and then after it works, I do a video. Well, it really doesn't tell you what goes on in the background. Each video set takes about a day, maybe just a couple of hours a day, but it takes time. And I think it's only truthful to actually show you some of those issues. So, recap: GCBASIC open source compiler. It's now going to support the Q20 chip family. It might support it out of the bag. I don't know. Hardly likely, because this is a voyage of discovery. Okay, recap. We got to look, just make sure we know where we are. This is like my diagram I use, and I say basically what we've got. I'll bring the pen up. We've got a thing called a compiler. We take your source code, we take a load of libraries, and we stick them into the preprocessor, goes through a code translator, assembles it, produces an ASM file if you need it, pushes it through GCASM, and produces an absolute machine code hex file. Really simple. Do you know what? That's what I've been telling you. That's not actually what happens, because there's more going on, and it's all documented. But you can't go to the depths of everything each time. But what I do need to explain is some of the challenges in getting things going. And this is these extra red pieces. Chips come with specific constraints. A new chip family will have different characteristics from previous chips. And those are facts. These are things you go find and experience during the implementation. And I sort of document those as I go through. And I go, there's a demo, it works, and here's some documentation to go with it. You might not like the way I document it. I do it so I can forget it, because the chip constraints are very important, and they're becoming more important. And I know that the Q24 has some strange constraints. Secondly, chip-specific DAT file. Well, that chip-specific DAT file has to match the chip. And they're created from XML files, and there's a whole process that goes on in the background, and we will expose that process that goes on, because it is quite interesting. I take XML files, I turn them into INC files, and then I produce a DAT file, and it might be wrong. And the only way to find out if it's wrong is to test it. And I produce 20 odd videos nowadays, and those are the tests. And they'll test things because we have to test. So once we know that we've got some chip constraints, and I don't know them because I've not used this chip before, and there's some chip-specific DAT file that has been created but not tested, that's where we start. And that's where I start. So what am I going to be using? I'm going to be using this. Okay, you've seen this in the videos in the past. Oh, it becomes out of order. Here is a 26 Q24 handwritten label, and in here I have got a PIC-Kit 2 attached to it. You have to believe me. There's 4 LEDs attached here, and this is the same setup I had for the 18F Q20. Yeah, yesterday. So look, in here, look, there were 4 wires connected. Oh, I want to put that on there. And they are left over from yesterday, from the Q20. And to be quite frank, they should work. Of course they don't. So you have to trust me that those 4 wires are connected to these 4 LEDs. And there's some circuitry that goes on the side of that. If you want this board, let me know. They're very expensive, but they're great because I use them all the time. Why it's important is because it supports 8, 14, 18, 24, 40 pin devices, has LED switches, pots, lots of connections. I use PICKit 2. I know the PICKit 2 works because I've tested that independently. Okay, so we have a proviso that it works. But so what? To be quite frank, I always test things. I test things extensively. I would use a PICKit 4 initially if I had any concerns, but I don't. It works fine. And I have an external power supply. All good stuff. So once we know that we've done all that stuff and you've sort of got an idea that we're going to try to get an LED to flash, let's get started. First of all, I'm going to go to the installation folder where I am doing all my work. So I'm going to go into PowerPoint, and I'm going to show you my PowerPoint because we're going to update this PowerPoint as we go along. I'm going to actually create a slide called Summary Findings, and that would be a good summary findings. Great. File. I'm just going to open the file location just to show you there's no magic going on. Here is my folder. You don't really need to see it. Basically, there's a PowerPoint called Chip Challenges, and there's nothing in its parental folder, which is called 18F XX Q24 chip range demonstration. Nothing in it. I'm starting afresh because that's how I do it. Okay. Let's just go down to Copilot. I think I asked Copilot to write me some programming yesterday. We'll just do it again. Here is a program for a Q20. Where was the question for that? This is what I was using yesterday. Write a program for the, I'll just make sure you can see this on the screen. Let me just shuffle the screen around a bit. There we go. I'll just shuffle that around so that you can see it. I'm just going to paste my question into here. I'm just using Copilot to save time, that's all. Write a GCBASIC program for a 26, that's my chip that I've got installed, Q24 that flashes an LED on port C7, 6, 5, and 4 every 100 milliseconds. Enter. Okay, great. So it's given me a nice program. I don't have to write it in reality. I can just take a copy of that. And it will, let me just scan it. Looks great. There we go. Demonstration sources, file, new text file. Paste that in. I'm then going to save that out to my folder. Save as. And I'm going to put it in the folder that I was just looking at. Let me just pull up that folder. There we go. And we're going to call this 001 test. And later on, I will come in and I will then do all this renaming, as I always do, .gcb. And I've just done all that, and I've put it in the right folder location. 001 test. So what we should expect is that the compiler will compile it up for a chip for 26Q24. All my variables will need to be defined, which they will be. I've got an LED on C7 to C4, which we have. They're all set to outputs, and we've got 100 millisecond wait. Right, function key F5. We'll see what happens. It won't do anything because this is the vagaries of doing videos, is that I've got the name wrong. It's .vb, and that won't work because GC code requires .gcb. All right, so how are we going to fix that? We're going to go into stay in GC code, don't panic. Control B, find our folder. Here's our, we can rename it once we've opened our folder. Let's go to our empty folder, open folder. I keep everything in a Git, so locally demonstration files are all in the same place for me. You could do the same, I don't really care. That's where my project is, Q24, and that's the folder I'm working in. I've just selected it. Now, it sort of creates a whole project folder for you, and there's my file on the left-hand side. Rename .gcb. Now I can just click on it, and it'll bring it into here. Control B to shut down that folder window. So there's my source code. It's all sitting there. very nicely. Program written by, not by me, but by machine, which is fantastic, really. Function key F5. Let's have a look what's going on at the bottom of the screen. Well, it's program, it's done lots of things. Let's have a look what it's actually got in there. Quite important. It says it's compiling my file called 001 test. It's compiled it in, it's obviously found the Q24 DAT file, because if it didn't find it, it would actually complain. It's compiled using GCASM, fantastic. Then it's passed it off to PitKit Plus for programming. It found the chip and it programmed it in 5 seconds. And then I get a nice warning saying, warning, this is a this is a development chip definition file, .dat file. It's not been validated. And that is true, because it hasn't been validated. And you'll get that warning whenever I haven't tested something, because when I generate the DAT files, there's a little flag that says this has not been tested. Let's have a look at what's happening on the camera. I'd already looked across there. There is no action. Why is there no action? Well, probably we'd all panic and go, it's the compiler's fault. Well, it's not. It's the chip constraints. Let's have a look how we're going to resolve this. Function key F4, open up PicInfo. All I'm going to do is use PicInfo to get the data that does. It's just a faster way to do things, to be quite frank. I'll bring it into here. 25Q24. I want the 26Q24. 26Q24. Open up the datasheet. Now, we're going to look at the datasheet because there are constraints around the way that this chip works. It's not like a normal chip. It looks like a normal chip to anybody else, but for those who know what's going on, it's not a normal chip. Okay, let me just take you straight down to where the issue lies. And I already know because of the Q20 issue I was working on. Let's just look at this diagram. I'll use this one because that's what I've got. I'm going to take a screenshot of that. Why? Because I'm going to paint on it. And I'm going to shove that inside my PowerPoint. I'm in PowerPoint and we're going to do this live, change the layout, blank, and paste it into here. There we are, there's the picture. Now what I can do is I can look at that and I can annotate it. I've got all the right connections. Trust me, I have all the right connections. We definitely have a master clear. We have a data line. We have a clock. Or we have a VDD and a VSS. Why? Because it programmed it. We know those things. It has the chip that the program I wrote inside of that chip. You have to trust me. I'll get a kit for it and prove it. I don't have to. The issue is these new chips come with power domains. And the power domain in this chip, I don't know why they use two colors, but it sort of makes sense. Okay. This orange chip here, look, says VDDIO2. Now that tells me there must be a VDDIO3 somewhere, but never mind, eh? These green ones here are down here. Look. VDDIO2 power domain. That means that 6, 5, 4, and 3 are all on a power domain that requires power. So you have to put a VDD supply on pin 20 and a VDD domain, that could be 3 volts, 5 volts, whatever voltage you select. You need to put it on it, otherwise the chip won't work. The chip is currently has no supply voltage into the VDIO2 power domain. It has it on the major power domain, but not in this particular one. Hence, the chip is sitting there stationary. Let's go out to the camera and see what's happening. See if I can get that working. If it doesn't work, I'm going to stop the video, fix it, and join the video in. I've got one of these prepared, but hold on a minute. I've got a problem here. Going back to my PowerPoint, I have a problem. Where's RC7? Doesn't exist. So I am not going to expect the LED on RC7 to work here, because that was where RC7 normally sits. So you just have to sort of trust me. I know that stuff off the top of my head. So RC7 is also the VDDIO2 input line. Okay, once we know that, we're going to have to sort of jiggle things around from the demonstrations that I was doing previously using those 4 IOs. So I'm going to, first of all, I'm going to take off the yellow one because that is on piece. You can't work it out here. It's actually all labeled down here. It's all labeled. I don't have to sort of hunt around. And on this board, on the right-hand side, I've got all the voltages and all the grounds. This is superbly designed. Okay. All I've got to do is sort of drop that. Oh, I'm not being very clumsy here. Drop that in there. And hey presto, nothing works. I'm genuinely surprised. 26. I'm looking back at my source code to see what's happening. I'm just reprogramming it to make sure that I haven't wiped it out. Stopping the video. I'll come back. Welcome back. So I know where the fault is. Let's get cracking. Let's look at my source code. Hasn't changed. Same source code. I have to reassure you that I'm doing that. I'm not going to show you the programming events anymore. You're just, oops, sorry. You're going to have to sort of trust me that I'm doing all that stuff. Okay, so when I say I'm pressing function key F5, I am. Okay. First we do Shift F7. We're going to look at the source, the assembler that was produced. Well, it looks okay. Lots of things in here about headers. Send me some money. Do send some money. We are running desperately short on the project at the moment. I'll go on to that later. First of all, look at this mess here. Set aside memory locations for variables. Well, should we look at the memory map for this chip? We'll go out to the data sheet. Cursor down. Find the memory page. I have been here so often. Page 73. Oh, it opened up a different browser. Never mind. Memory. I'm looking at the RAM, not the physical registers. Here it is. Here's the memory map for this thing. I'll zoom in as much as I can to make it readable for you. There we go. We're looking at a 18F 26Q24. So it's this column here. And it says that you've got fast SFR between this register here, and that your access RAM or your RAM is the green stuff, which is from hexadecimal. I'm gonna do it in hexadecimal, but you're gonna see decimal numbers. Okay, so this is 5 hexadecimal 500 to 5FF, and then there's a block from 60 to 6FF. So I don't know why they've done that in the documentation. It does make it rather confusing, but never mind. If you look at 6, there is a block of RAM from 600 to 6FF, and it goes down for our particular chip down to here, which is 20 in decimal, but 14FF. So really, the RAM in this chip, the RAM in this specific chip, not another chip, lies between 500 and 14FF, which is 14 is 20 hexadecimal, 14FF. And the DAT file is wrong. I just checked it, okay? A way of checking this out is here's a way of checking stuff out. Come into your favorite search engine, type in 18F26Q24, JLlib. My buddies over at JAL, we do sort of work together. Here is JALlib. Go into the includes, go into the devices, Control F, 26Q24. Oh, they haven't done it yet. Have they done any? Oh, they've done a Q24. They've done one Q24, look. 25. Oh, there it is, that. 26 Q24 is what I'm looking for. And in this particular file, wherever it is, oh, there it is, you can just confirm things. Look, in here it says it's got shared RAM, shared, here's the data, here's the RAM, look. Let's zoom in on that for you. 500 to 14FF, which is what I just said for the data sheet. And it has shared RAM between these locations. And shared RAM is fast RAM. And that's why we get differences in the initial ASM that's incorrect, is because the compiler hasn't got the right information. It knows there's some fast RAM, but it's actually got that address wrong. And address 1 is not in RAM. It's actually in the hardware. It's in a register. Let's look at the root cause of the problem. I'm going to open up a file. I will do it slowly. I could do it quicker, but I won't. Into my compiler setup, GC Studio, GCBASIC. If you wondered, do I run the same system as you? I run exactly the same system. 18F 26 Q24. There's the DAT file. Open it up. And in here, it's got the free RAM. And the free RAM is set to 00. Well, we know that's wrong. We know that's wrong because it's been wrong in the generation process. That is correct. And is this correct down here, look? 500 to 5FF, 460 to 4FF. Well, we can look at the JAL stuff. Oh, it's the same. Look, that bit's correct. This part was wrong. The RAM location was wrong. Save that. Now, we have not fixed the root cause of the problem. The root cause of the problem is in the generation of the DAT file, and I will do that separately. So I've made a note that in my PowerPoint in here, the initial challenges, which is what I'm updating, is that the DAT file was incorrect. RAM location, not shared RAM, not just the RAM location. So that tells me I need to go and do that later on, so I don't forget it. Whilst we're in the DAT file, I'm just going to come into here, search for the word test, and I found the entry for not tested. I'm just going to put that to 0. Why? I just don't want to see that again. Okay. I'm going to save it. So all I've done is change the DAT file. Function key F5 program. Let's go into Zen mode. We have 4 LEDs flashing. Oh, we don't. We have 3 LEDs flashing. That's because port C7 is not a valid output. So that's okay. We're going to change our source program, and then we'll jiggle things around, and I shall be happy for one day. Okay. I might rue this. I might have to come back and do a bit more analysis on this later on, but I'm going to change it on this demonstration to port C0, 1, 2, and 3. Copy. Looks great. This is the way to write code. What's the right? Change to rotate LEDs. Oops, sorry. Oh, there we go. Great. I just want to rotate the LEDs to make sure they're actually working. Paste that in. Back to my desk cam. So I'm going to shuffle everything down in here. Leave the volt. You can see it here. Leaving the voltage domain as it is. I'm just going to shuffle down these onto 0. I'll just take the power off really. This is a header you can see I'm playing with here. Now these might work. I'll have to give it some thought later on. That looks correct. We won't get any action until I reprogram it, of course. Function key F5. All I did was paste that piece of code. Woo! Woo! I didn't copy all the code, look. No, I didn't. It actually probably hadn't actually completed its task. Not very optimized code, but it sort of works, yeah. We have 4 LEDs rotating as per the specification in Copilot. So let's look at the ASM. Now the ASM is now correct. If you can see in the ASM, remember this one here was in the wrong memory location. That's because the DAT file was wrong. We have a working compiler. And everything else sort of shuffles into place because most of the libraries can cope with this chip. It just knows about this chip. We have a quick look in here. Init.sys is the important part. Forget all this LED stuff control for the time being. The important thing is that I test the frequency and that the frequency specified in the chip is actually working at the specification. I will do that at a later stage. But essentially, it's coming into here and it's setting it to the internal oscillator, which it should do. It's clearing it down. It's setting it to 16 megahertz. I can put a scope on this in a minute to make sure that's working. And what I'm looking for is that 100 millisecond delay. Sets up all the COM ports, etc. Now, for the observant in there, there was a bug, not a bug, a feature. The compiler allowed me to put a port C.7 in there that didn't exist, and it didn't moan. It didn't complain. So I'm going to have to figure that out. That's a compiler change. That's not a bug in the DAT file. That's a compiler change. There's something amiss. Why did it let me put port C.7 in when if I change this to, I don't know, I'll put a G in here, compile it, it will complain. It will say, oh, your constant doesn't exist. Because it doesn't exist. But why? I think what the compiler, Hugh did when he's testing, he's actually tested for the port, not the port bit. And I might go back and change that later on. So back into my PowerPoint, I shall put that code as it was. Back into my PowerPoint. Compiler does not handle port.bit appropriately. And I'll go back and undefined, because port C.7, well, port C.7 did not exist, does not exist, okay? And I can sort of prove that later on, but that's my gut feel. Well, I know that from the data sheet. So what have we done? We've flashed some LEDs, compiler's working, DAT file was wrong, and we'll be back changing that DAT file so many times over the next 21 days. It takes 21 days to do the videos. So I will go offline, and I'm going to change the, I'm going to go and change the DAT file generator, do that offline. That's up on GitHub as well, in the data file area. And all it is, it's just a switch I have to actually put in it, so it's actually, I've got the memory correct. Why don't we have a look at it to see what's gone wrong? It's in Excel, for those who don't know it. And the file I want is called AVR chip data. And in AVR chip data, it has all the chips. Oh, it's hundreds, thousands of them. For those who don't know how to use Excel, I'm not going to teach you. Oh. Test filters contains Q24. Am I looking at the right file? File open. I'm going to close that down, dump it, and just do it properly. Let me just go into, I'll go into here, open up another window, D drive, the gits, DAT files. Chip, I opened up the wrong one, I think. Chipdata.csv, just for those who want to see it. Chipdata.csv. Data, tab, filter, and then you can sort of drop on this triangle here to Q24, because there are a few in here. There's the list of chips. Let me have a tap on there, and it will just open it up. Q24, and I'm going to look at the specification of it. And if I move to the left, you can't see it, so I will just change Excel for you. I wonder if that will work so you can see it all. Oh, there you go. I'm looking at it now. Oh, that's weird. That memory location is correct. Oh, I know why. So the actual generation file itself looks for a particular flag. That flag is not there. I would go offline and change that, and I will generate a new set of files for the Q24. Bye-bye. Back in a bit. We left it, I was looking in the chip data Excel file. And quite rightly, the issue is not in here. This specification is great. So it basically says that it's not tested. Let me put that to 0. I'll leave the others as 1 because we are testing that particular chip. It's a chip family 16111, and it's a special flag that can be used inside of your program. And a lot of this data is actually exposed inside the DAT file for obvious reasons. And there is no error in here. There's nothing wrong in this file, but I will save it just to prove it to you. The issue is actually in the source file that there's another program that generates the DAT file, does all the conversions, and it was in here. And it's a little bit naughty because we hard code this because no one gets to use this, okay? And you don't get to see this normally. And it says in here, and I'll show it to you. Imagine it said this, look, if the chip name has a Q20 in it, do something. If it has a Q43, do something. And it's all the new Q chips, right? I don't know why, looking at it now, I think a test of Q would be enough. And it says in here, the chip minimum select value is 5. Remember back to the data sheet, it said the minimum page was 5. Good. And then it goes here, look, here it is. Here's the answer. Look. It says the minimum page is 500 to the chip RAM size. Minus less 1 byte plus. Oh, it's confusing. It's not hard. Chip RAM size minus 1. 1280 is 500 hex. My brain just hexadecimal to decimal. It just works at that sort of high speed. And so basically, it's going to set what's called an RBC, a RAM block, and it will then enter that RAM block into the compiler not the compiler, in the generation process, and magic happens. Save the file. Let me go out and just show you exactly what I'm doing. DAT file generator. I'm just going to open a terminal in there. A terminal is like an old command window. There's a command window, clear screen. So I'm just going to say FreeBASIC, and FreeBASIC is installed in this folder, so I don't have to go hunting around. Get chipdata.bas, and that was the file I was just looking at. And it's just compiled it. Get chip data 18F 26Q for Q24. 24. It says it found it. It was the 687th entry of the 1135 chips it found. It gives you some other information about stuff it's ignoring, which it does, which is quite valid. And then it sort of drops at the bottom and says, fine, done. So what did it do? What did it do? Well, if we go into chip generator, there's a load of folders in here. I'm going to ignore all the other issues, okay? All right, because they're not important at the moment. Inside of here, there's chip data. And the top file in there is called chip data, by the way. It's the same folder that's in your installation. And if I looked in there, I could figure out what changed, but I don't have to because I have GitHub installed. So I'll start GitHub. And I'm going to ask GitHub to tell me what the difference is, what changed in that file. So what changed in the DAT file is shown in this screen. Let me just see if I can make that a bit better for you. Oh, there you go. It said I changed, not tested, and it got changed to something different, which is not tested equals 0, which is fantastic because we know we did that. We did that. We did that. We asked it to be changed. And in here, you can now see it on your screen, because I'm looking at slightly, it's corrected the RAM for us. Oh, now is that true? I don't think, oh, wait a minute, we can have a look. Oh, it was that, it is now this. And that's the change I wanted to see. There have been other tweaks, and those tweaks in this file will be because it's picking up the latest files from Microchip. It automatically does that in the background. But the part that I'm looking for is whether this memory address is correct. So if I look inside of here, take a copy of that file, go back to my hard drive, my local hard drive, which is this folder here. I'm using the latest version of Windows, so I can sort of change between the tabs here quite at high speed. Control V, paste that into there, replace the destination, it just put it in there. Go back into GC code, wherever that is. It's on my screen here. We can have a look in that file. Did it change? Well, if we do a search in here, not tested will be set to 1. Let me just do a search, test. Oh, no, because when it's not a test file, it doesn't exist, so it doesn't exist. Let's look at the RAM locations. Free RAM, is correct. And you might think, he didn't do it. I did, honestly, I've done it. Now I can then use that chip file, and it will work. Now you can see in the source file of getChipData.bas, it says M on it, which basically means it's been modified. I need to upload that to GitHub to make sure that everything is good. All right. So I will close that because my GitHub engine, your GitHub engine, if you used it, you just upload it. All right. Okay. I can now come into here, confidently press function key F5, confidently go to Zen mode, and the LEDs are flashing. We'll look at the ASM to make sure that's okay. We'll look at the top of the ASM. These addresses are correct. They're sitting in the right hexadecimal location. So these things in the ASM that exist, like this hexadecimal addresses, I've added in the last year or so to make diagnosis easier. I don't have to sort of figure it out. I go, oh, that looks correct. Instantly, I knew that that's where the problem lay. Back to my PowerPoint. Resolved. I have resolved that issue. Discard that. That is resolved. So, yeah, fixed within get chip data.bas. I'm sure we'll be back in there later on, having a little hack around there later on. This here, do you know what? Low priority. I'll come back to that later on. Okay, that's quite not important to us at this present moment in time. I can now go away, and I will go away, and I will install the hard. Let's just sort that out. Install the hardware and make the board work and flash 3 LEDs. I've actually flashed 4. This is fantastic, really. And I'll give it some thought whether those ports C0 to C.3 are going to be good enough and flexible enough to allow me to do a full set of demonstrations. I have to get in the serial lines. Well, I know there's a problem with the serial already. I can tell you that now. Look, watch. I can tell you there's a problem in the serial line. Let's go down to mine. Because historically, bring up the pen, and this will confuse a lot of people. A lot of people are going to be genuinely confused about this chip. This and this line here Well, they receive serial USART and transmit USART. They're going to be genuinely confused. They're going to go, well, I plugged this chip in and it didn't work. Well, of course it didn't work because you got a whole power domain on what used to be RC7. So this is not a really compatible chip. So I'm going to think about this and go, oh, right, let me just clear this. Erase all link. I have already sort of decided, and we can do a test on here. That's good. That's one LED. That's two LEDs. That's three LEDs. It won't work. I'm going to need to tell you that because I'm not going to cross domains with I2C. I'm going to keep all the things to do with I2C in one domain. So I will just think about this a bit more. I put I2C on here, and probably I'll get SPI on here as well. This is great. I will put RC6. Is that the normal line? Let me look at my wall here. That's the transmit, RC6. Yeah, is that normal? No, RC6 is transmit. I'm going to put RX on here. I need RX later. TX here. I'm going to use 3 and 4 for and SPI. Good. Up here, I will put a pot on RA3 or RA3. I will put a switch, pot, switch. So that means that takes me to this one here. Oh dear. I might have to go and figure this out a bit more. I'm going to put my LEDs on here. That'll work. That's what I'm going to do. So in the demonstrations, I'm going to change everything to a B, port B, 0, and that should work in terms of demonstrations. This chip is going to really blow some people's minds, okay, when they get it. Okay, all right, like and subscribe this video. This is the new chip family, getting the basics operating. This is not your normal video. I will do the normal video later on when I've got a minute. I'm going to go and have a coffee. Enjoy.